This chapter involves alkenes, the first compound that has a carbon-carbon double bond. And also will deal with elimination reaction, which is needed in order to make the alkenes. So we talked about nucleophilic substitution briefly in the previous chapter, and then we are going to talk about elimination, and then kind of combine both types of reactions here. And these are the important part of these chapters where we talk about reactions, their mechanism, what are the differences, what are the conditions and things that could change in one reaction become a completely different types of reaction. Those are the kind of things that will tie all of them together. And later on, we're again going to deal with that in more thoroughly in chapter 8. So these are very important topics and pay attention to that. Now, we'll talk very briefly about the physical properties, and so then jump onto the actual elimination reaction, which will actually probably start the elimination reaction on Friday. Okay, so alkenes are essentially generated from alkanes, where you introduce the carbon-carbon double bond. And the nomenclature also involves a replacement of ANE with ENE. So the very first member of this group would be CH2CH2, which can be derived essentially from alkane would be the ethane by removal of the two hydrogens. If we remove two hydrogens and form a carbon-carbon double bond, that would be then become an alkene. So this is now, its name is ethane with ANE, and so the IUPAC name for this is ethene. But this has been known long before IUPAC was ever formed, so the common name, which is actually more commonly used for this compound, is ethylene. So this is the common name. Likewise, from 3-carbon unit, where you have a propane, 3-carbon state unit, you get propene. Again, ANE is replaced with ENE. As soon as we go to butene, of course the double bond could be in different places. So from butane, which is 4-carbon unit, we can have one butene, which is the first carbon joined with so this is one butene. Because the double bond is between 1 and 2 carbon, we don't say 1, 2, because it's obvious that the second carbon will have also double bond. Okay, then we just name the alkene according to the first carbon that joins. So this is actually 1, 2, 3, 4, and the double bond is between 1 and 2. If we move the double bond, then there's a consequence of generating stereoisomers as well, because you can have, if we write that 2-butene this way, this is 2-butene, but it can exist as 2 stereoisomers because we can have a cis or a trans. Cis 1-butene obviously the relationship, we also know that between 1-butene and 2-butene, they're constitutional isomers. So between 1-butene and any one of these two, they would be constitutional isomers, and the relationship between the 6 and trans 2-butene they are stereoisomers. Okay? So these two are stereoisomers. Now, if you have substituents there, then you have to kind of also look at the hierarchy of the different groups. Okay. So, in terms of the priorities, the carbon-carbon double bond has a higher priority than the alkyl group and the halogens. However, it has a lower priority than alcohol, OH. So the priorities are essentially, this is the order. You have OH group, okay, the carbon-carbon double bond, then you have the alkyl group, and halogens. Essentially, this is 1, this is 2, and this is 2. That's how the priorities are. In other words, if we make up a molecule, let's say, molecule like this, in this case, of course, we got to start counting from this side and not this side, because the halogens have a lower ranking here. So this is therefore 1, 2, 3, 4, 5. So it's a 5 carbon unit. So it's 1 benzene, but you have a 5 position has a fluorine group. So it's 5 fluoro. 1 benzene. Now, if you have an alcohol group, however, then the number would be switched, because the same compound, if we just replace the fluorine with the OH, then this becomes carbon number 1, 2, 3, 4, and 5. Now, we always indicate the in group that the first carbon to which the double bond is attached. So this would be actually 4 position where the carbon-carbon double bond is, and therefore this becomes now an alcohol unit. But we have both in and all. So we have to name it accordingly, which means that it's you could say pent 5 in 1 all. Okay, that's one way to name it. Yes. Oh, sorry. This should be 4. We need that. Pent 4 in 1 all, or 4 benzene 1 all. Either name is acceptable. One was introduced in, this name nomenclature was introduced in 1993. From the 70s we used that 4 benzene 1 all. Okay, so you also can have cyclic molecules with that, and again, you do the same thing there. If you have cyclic molecule, and let's say have a methyl group here, then again you have to name the alkene unit as 1, 2. So therefore, we cannot start from here. We have to start from this side, which gives the lowest number to the other substituent. which means that this is a 3-methyl cyclohexene. And if you have multiple groups, then of course you also indicate. In this case, it's implied that one position has the carbon-carbon double bond. In other cases, if you have multiple units, then you also indicate where the double bond is being produced. All right, so the other part of the nomenclature is that if you have a carbon-carbon double bond, as we know that you may have different groups attached to them. And we know that we know how to name them as cis or trans depending on if they're on the same side or opposite side. However, if the groups are different, then what happens? So let me make up something here. Let's say this group is so now it becomes an issue of how to actually prioritize these different groups. So the priority rule was developed by Kahn, Ingold, and Freelon. So the priority would be given based on first the atom attached to it. If they are different, then you go to the higher atomic number. So the first is that, first of all, what you have to do is to divide it into two parts. So with respect to the double bond, let's say there are two parts. And we compare the two here and here. And first rule is, of course, the atomic number. All right, so between these two, this is attached to carbon, and this is attached to chlorine. Chlorine has a higher atomic number. So then this one gets a higher end. This is lower. It doesn't matter how long it is. It's the main attachment to which the attached to the carbon double bond. That's the important part. All right. Now between these two again, the same thing. You have bromine and a carbon. So the bromine has a higher atomic number, so this gets a higher rank. This is lower. Now, based on that, then you have a higher and a lower across the double bond, and the other side also like that. It is kind of like trans, right? Except that now we cannot call it cis or trans. Cis or trans were related to same groups, like methyl or ethyl, whatever. So now we call them as Z. This comes from a German word called zusammen, which means together. When two higher groups are on the same side. Or E, which is actually another German word called Angegeben, which means that they're opposite. When higher and here, if we do this after doing the characteristic, lower and higher group on the same side, all right, which means that this is an E compound. The rest of the nomenclature goes according to the substitutes that you have. But this is an E compound, right? Now, what happens if you have the same atom in both cases? And let me give you a couple examples of that. So I made up a bunch of groups here, and now how do we determine that? In both cases, they're connected to a carbon, right? And they're also connected to two hydrogens. So the important part, the way we establish the priority, is that we rewrite this. Let's say the C is attached to an oxygen here, and then you have two hydrogens attached. And this C, on the other hand, is joined with a carbon and two hydrogens. And the first point of difference is the one that makes the difference. So the oxygen is the important part. Compared to carbon, has a higher atomic number. Therefore, this is a higher. This is low. And then again, let's look at the other side. The other side, you have a CH2O CH3. So again, this carbon attached to oxygen, hydrogen, hydrogen. This one is hydrogen, hydrogen, hydrogen. Therefore, this one gets a higher priority. Which means this is a Z compound. This is lower. The higher and higher on the same side, and the lower and the lower on the other side. And there are some other issues related to that. If you have multiple bonds, then you can count them multiple times. And let me give you an example of that. So in this compound now, to determine whether it's a Z or E, again we follow the same rule that we gotta look at each side separately. And we look at this carbon. Now this is connected to two hydrogens and a nitrogen. This is NH2. So this is C, N, H, H. And this one is C, O, H, H. And oxygen and nitrogen, if we can see that oxygen has a higher atomic number, therefore this is getting a higher priority. Now on the other side, you have a CH2OH. So this is connected to OH, H. And this one has a double bonded oxygen. Therefore, we got to count the oxygen twice. So this is COOH, which means that this one has 2 oxygen rather than 1 here. This gets a higher priority. This is lower. And therefore higher and lower on the same side, so this is an E isomer. Is this concept clear? There's a priority rule. You first look at the atomic number of the attachments to the double bond. Then, if they're the same, then you go one more step and see what else they are attached to. Sometimes they may have to go 2-3 steps if it is a long chain and differentiate them based on what else is attached to them. And then figure out higher and lower priority and then see whether Z or E isomer. Now, in case of alkenes with a cyclic molecule, okay, most of the time what we are going to see is for small groups, the attachment is actually cis, because this hydrogen and this hydrogen are on the same side, and these CH2 groups are on the same side, so this is cis. If you have other attachments also, they would be like a Z or E, depending on that. But can you introduce a trans double bond? It turns out that trans double bond introduces strain on the molecule for a small cyclic molecule. However, at 8 carbon, if you have 8 carbons, then you can have a carbon-carbon double bond introduced there. So how do you do that? Like, let's say, draw them. So this is actually 1, 2, 3, 4, 5, 6, 7, 8. You can have a double bond there, so the hydrogens are on the opposite side. This is a trans double bond. And of course, you can also have the same type of molecule where you have cis double bond. So just move the double bond somewhere else. So this is a cis double bond. And it turns out that obviously because of the strain involved with the trans double bond in this 8-member ring system, this is less stable than this one. Okay, this is more stable. But as the rings get larger, then they can accommodate a carbon-carbon double bond that is trans. And it is even possible to generate one in a 7-member, 7-carbon ring system, except that they are only stable at like -92 degrees. Otherwise, they'll fall apart. So the carbon-carbon double bond can be cis or trans or Z or E, depending on the variety of factors, and of course, the cyclic molecule that introduces angle strain in the molecule. Any question up to that? Nomenclature and the GNC nomenclature. Yes?
Is there a point where the trans will become more stable than the cis?
At what point what?
Is there a point where the double bond in the cyclo unit will become more stable than the cis?
Yes. If it gets to, I think the size is about 14 or 15. It gets large enough that the angle strains are minimal, and typically the trans double bond has less van der Waals interaction. We're going to get to those points in a minute. But in general, the trans double bond has less van der Waals interaction, as you can expect. And you have a group here and a group here. Let's say this versus this. because the two large groups are on the same side, in the states, you'll have more van der Waals interaction. Typical. And trans, therefore, is more stable in those cases. And the cyclic molecule is reversed because of the difficulty of generation of trans structure. And then it has to be large enough to avoid that. Yeah, in six-membered ring, in order to introduce a double bond, it has to be 6. Otherwise, it's impossible to maintain that angle strain is too large, so they don't form. In fact, in 7-membered ring, it was created, but that compound is stable only at minus 9 degree falsified. All right, so we can see in terms of the physical properties. All right, so we'll